we present AWAC, Accelerating Online Reinforcement Learning with Offline Datasets. How can we learn difficult tasks with little online fine-tuning by using prior datasets? Consider this door opening task. Prior data to solve the task may be available as off-policy data from expert demonstrations or from prior runs of RL. Prior work has considered offline RL, which maximizes expected returns using the prior dataset but without online interaction, and this may solve the task partially. But often, online fine-tuning is required to truly master the task. We will show that our algorithm can be used to solve these difficult dexterous manipulation tasks very sample efficiently. It solves this door opening task in under 1 hour of online interaction. We first study offline learning followed by online fine-tuning with existing methods. We find 3 shortcomings with existing algorithms in this setting on the half-cheetah v2 environment. The prior dataset we use is shown in the videos above, a mixture of 15 expert trajectories with 500 lower quality trajectories generated by behavior cloning. The first shortcoming is data efficiency. On-policy methods exhibit slow online improvement. Both AWR, which uses on-policy value estimation, and DAPG, which was used for fine-tuning from demonstration data, are relatively slow to improve online. Our method is superimposed to show how fast improvement could potentially be. Since we want fast online fine-tuning, we will focus on off-policy actor-critic methods. However, we find that actor-critic methods struggle in offline training, even if the policy is pre-trained with behavior cloning. Above, we see 3 examples of soft actor-critic. The blue curve is pre-trained on prior data, but we see it is no faster than the green curve, which trains from scratch. Even if SAC is pre-trained with behavior cloning, shown as the brown curve, the policy immediately deteriorates during online fine-tuning. Actor-critic methods can be stabilized for offline training by incorporating a policy constraint in the policy improvement step. The standard policy improvement objective maximizes estimated returns. Prior methods have investigated adding a constraint to stay close to the data distribution, which allows successful offline training with actor-critic methods. However, as we'll see next, prior methods have trained a behavior model, pi beta, by supervised learning, which poses a challenge in the online setting. Above, we see an example of BEAR, an offline method which enforces a constraint during the policy update, struggling to fine-tune online. When the constraint is loosened, the offline performance is worse, and fine-tuning is still relatively slow. The plot on the right shows the log likelihood of a behavior model which is pre-trained offline and then continuously trained online, split between offline and online data. We see that online training causes the behavior model to struggle to fit the offline data, and that the online data has even lower likelihood than the offline data. To address these challenges, we present our method, Advantage-Weighted Actor-Critic, or AWAC. Our method incorporates a KL constraint into the actor-critic framework implicitly. This results in a policy update that resembles supervised learning. AWAC trains well offline, fine-tunes quickly online, and does not require estimating a behavior model. We evaluate our method against prior methods on a suite of dexterous manipulation tasks. These tasks exhibit high action dimension, complex contact forces, and sparse rewards. For each task, we begin with a prior dataset of human demonstrations and off-policy data collected by behavior cloning on those demonstrations. As you can see, the behavior cloning is not very successful in many of these tasks. On this door opening task, we find that AWAC begins at reasonable offline training performance and then learns quickly online. After 300,000 time steps, which is less than an hour of real-time experience, AWAC has nearly mastered the task. Here we show the performance of prior methods on this task. Shown on the top right is the success rate after 300,000 time steps. Only AWAC consistently solved the task. This object relocation task is especially challenging for prior methods to solve. We can see that after online fine-tuning, AWAC successfully grasps the object and brings it to the target location marked in green. In comparison, no prior method makes significant progress on this task. This in-hand pen rotation task is relatively easier and can be learned to reasonable proficiency by offline pre-training. But we see that AWAC performs best after fine-tuning compared to the prior methods. We next evaluate our method on suboptimal prior data generated by a random process in a Sawyer manipulation environment. The random data is shown here, and note that the actions are independent of puck goal position, shown in red. We find that our method quickly learns the task from fine-tuning from suboptimal prior data. After 100,000 steps of online fine-tuning, it achieves a success rate of 90%. So now that we have an algorithm for fine-tuning from prior data, can we use it to solve real-world robotics problems? We evaluate on 3 challenging real-world domains, where in each domain, the prior data is a mix of human demonstrations and behavior cloning data. In this domain, the declaw robot is tasked with turning a valve 180 degrees from a sparse toward. We see in the learning curve that AWAC begins at slightly above behavior cloning performance and then improves steadily, while other methods that utilize prior data do not improve. These videos show the performance of each method after 20,000 steps of online experience. AWAC consistently solves a task while others do not. In this domain, the Sawyer robot is tasked with opening a drawer with a hook attachment, again with a sparse reward. For online learning to be effective, the learning algorithm must leverage the prior data to learn a policy that sometimes succeeds and an accurate value function for improvement. We see in the learning curve that AWAC is the only method that improves. In these videos of the algorithm performance after 40,000 steps, or slightly more than 1 hour of online experience, only AWAC consistently solves the task. In this domain, the most challenging, a 4-fingered robot hand is mounted onto a Sawyer robot. The task is to reposition the white object to the center of the table. Again, we see AWAC steadily improves from the initial pre-trained policy. Videos are shown after 50,000 time steps of real-world experience. The AWAC trained policy consistently grasps the object and repositions it. The behavior cloning policy generally has the right shape, but often it fails to hold on to the object. SAC from demos and SAC with the behavior cloning loss fail in this amount of time to learn the task. Moreover, they learn policies that flail the fingers dangerously, an artifact of the offline bootstrapping issue.